Welcome to day 17 of my AVR Advent Calendar. In this series of videos I show you in 24 days how to program AVR 8-bit microcontrollers. Last time we have programmed our Atmega 88PA microcontroller to act as an SPI slave, but currently we are missing an SPI Master to test it. So let's see what's in paperback number 17. Okay, cool. So here we have another AVR microcontroller. This time it's an A-Tiny44 microcontroller. And today I will show you how to use the universal serial interface of this microcontroller to act as an SPI master and to control our slave here. Okay, so first let's talk a little bit about the A-Tiny microcontroller. So here I have opened the datasheet with the pin out. So you can see it only offers 12 GPIO pins, and it doesn't have so much interfaces like the Atmega microcontrollers. So for example, this microcontroller has no dedicated SPI or I2C IP integrated into it. But instead, it has the universal serial interface. And you can use the universal serial interface to rebuild all the important serial protocols. So you can use it to act like, you can use it for UART, for SPI, or for I2C. And today I want to show you how to use this universal serial interface as an SPI master. So here in the datasheet, let's go down to the universal serial interface section. And here we can see how it's built up. So basically we have the following registers. We have a data register, we have a status register, and we have this control register here. And something important, we could use a 2-wire or 4-wire mode. And for shifting out data from the data register, we can use various triggers, and one trigger is, for example, this timer 0, but we will talk about this a little bit later. So let's go down to the registers. So what we will do is we will use this 3-wire mode we can see here, and we will use the master operation. So in the master operation we will shift out the data to this digital output. The data will come in from the digital input, and we will generate a clock over this US clock pin here. So this datasheet gives us some examples how to use this interface. But let's go down to the registers. So the first register is the data register. So when we want to write data out, we have to write the data in here, and by reading it back, we can read back the data which was received. So then we have the status register. And the important thing here, the first 4 bits here are a counter value. So here we have a counter which counts every rising and falling edge of our clock signal. And if this counter reaches 16, a byte was shifted out, and it will assert the interrupt flag here. So the counter overflow interrupt. And this way we can detect if a transfer is completed or not. So if we want to use I2C or UART, we would have a start condition interrupt flag. So this thing can detect if a stop condition is sent, but yeah, this is not important for us now. All we need is this counter here and this counter overflow flag. And here in the control register, we also have some interesting bits. So over bit number 7, we can enable an start condition interrupt. Bit 6 will enable a counter overflow interrupt. Over bit 4 up to 5, we can set the wire mode. So for example, we could set it to 3-wire mode, 2-wire mode for I2C, 3-wire mode for SPI, and that's basically it. And then we have a clock source select, because I already told you the clock can be triggered by various things. So what we have here, we have an internal clock strobe pin, and if we want to use this, we have to use this setup here. If we want to use timer 0, we have to set it up this way here. And if we are using it in a slave operation, we want to count up the counter on a edge coming in from the pin, and then we would use one of these configurations here. But next video we will talk a little bit about SPI slave mode, and there we will need these pins or these options down here. Today we will just use this software clock strobe option here. And this, the last bit, bit 0, is the toggle clock port pin. So here in the master mode we have to toggle the clock manually, and we can do this by writing to this bit here. Okay, so now let's take a look at the hardware setup. So here it is. Here we have our Mega 88PA microcontroller, which will act as an SPI slave. And here we have our A-Tiny44 microcontroller acting as an SPI Master. This pin here will be our chip select pin, and therefore I have selected port A pin 7. This pin here is the master input slave output pin, which is connected from this pin here, which is PA6 to the master input slave output pin up here. This pin is the data output, which is connected to master output slave input here. And this here is the serial clock coming from the A-Tiny44 to the Mega 88PA microcontroller. Okay, so much for the setup. Now let's start programming. Okay, so let me see into my AVR Advent Calendars folder. And yeah, what are we going to use for a template? This time it isn't so easy. Yeah, let's just use the first program here. And I will create a new folder, 17 USI SPI Master. So I will cd into this new folder. And first I will adapt the makefile. So the default frequency of this microcontroller is 2 MHz, and our device is now no longer an Mega 88PA microcontroller, but an A-Tiny44 microcontroller. And our target name should be USI SPI Master. Okay, so now let's open up the main file here. Okay, this is just the very simple main function here. So yeah, let me open up a little bit more up-to-date function. Yes, and here I can copy these 3 headers here. I don't need interrupts here in this example. Okay, so first let me define some pins and ports. So I will define the port SPI as port A, and the data direction register SPI to data direction register A. Then we have the USI serial clock pin, which is PA4. We have the USI data out pin, which is PA5. Data in is PA6. And chip select is PA7 here. And I will also define a macro for setting and unsetting the chip select. So first unset chip select is port SPI or 1 shifted by USI chip select. And for setting the chip select, I will end this with 1 shifted by USI CS inverted. Okay, then I will need a function for the SPI transfer, and I will call it SPI XFER. And uint AT data is the data we want to send. So the first thing we are going to do is we will set the chip select. Then we will load the data variable into our Universal Serial Interface data register. Then in the status register of the USI, I will clear the counter overflow interrupt. And then I will check as long as the status register and 1 shifted by USI overflow interrupt is equal to 0. I will then manually toggle the pin, and therefore I will write to the Universal Serial Interface control register and here I will set 1 shifted by USI mode 0. So this is wire mode 0, so this means free wire interface. Then I will need 1 shifted by USI CS1, 1 shifted by USI clock. So this is the selection we want to toggle the serial clock when the toggling bit is set. And last but not least, we have to do the toggle, and therefore I will use the toggle clock bit here, and that should be it. Then I will unset the chip select here, and I will return the value which is now in the USI data register. Okay, so now here in the main function we have to set up everything, and I will need a counter variable, or let's call it display. Okay, and then I will initialize the pins. So first I will set the USI data input pin to an input, and then I can set the other pins to outputs. So the data output will be an output, the USI clock will be an output, and the USI chip select will also be an output. Okay, no, I think it's S clock. No, USI OS. Okay, now it's okay. Okay, so now we have set up everything. So first we will do a read current displayed value. Therefore I will do an SPI transfer, and I will write out the command 11, which is return the register. Then I will set display to SPI xfer. This time I will just write out f's, and the value I got back should be the value which is currently displayed here on the display. And I will add a 1 to it, so I will increment it. Okay, now I will set the new value to display. So I will copy this 2 times 0. So first I will write out to 2 hexadecimal, and then I will write out my display variable. And down here, let's do a delay milliseconds. So let's update the display every half second here. Okay, so that should be it. Let me try to build it. This looks good. And before I do the compiling, I have to do the wiring. So give me a second so I can wire this up here on my breadboard. Okay, so before I complete the wiring, I have to do the flashing. And here I have to change a little bit here in my AVR Advent command. So now my target is no longer the Atmega 88PA, now it's the A-Tiny44. And the file I will flash is USI SPI Master.txt. Okay, so let me try to flash this. Okay, it looks good, it's flashed now. Now I will finish the wiring. Okay, the wiring is done. Now let's check if it works. So I will plug in my power supply, which is also coming from my USB ASP programmer. And yeah, now the value in the display is counted up every half second. Cool, so that's how to implement a USI SPI Master by using a A-Tiny44 microcontroller. I hope you've enjoyed the video and learned something, and I hope I will see you tomorrow. Bye!